This is Kosmographia, the Randall Carlson podcast. And welcome back, ladies and gentlemen, to Kosmographia, the Randall Carlson podcast. We have a very special show for you today. Brad, why don't you introduce our guest for us?
Well, this is Jerome Lesemann that we've been talking about for quite a few episodes. Come to talk about Drumlins. I met him back in 2009 at a GSA field trip into the Scablands. So we were in the same van, and I got to hear a lot of the alternative viewpoints of what we were seeing versus the standard story from some of the leaders of the trip that I guess it was 4 or 5 days. Yeah, so we spent quite a bit of time together. So then he's from now with the Vancouver Island University as a teacher there also, and was good enough. Randall's brought up in 2017 to spend 4 days with us. And took us up into the Drumlin fields on the Thompson Plateau. And we got some pictures, and I'm sure he's got a bunch of cool maps, which I love. And we're going to get into who knows what all. But Drumlins is the starting point. And, well, Randall will tell you later, there's a Drumlin behind him. There's Drumlin behind me. And then we got a Drumlin expert. So that's the big topic for tonight. All right. Jerome, welcome.
Thank you. Thanks for having me. I'm happy to be here. Always good to see you guys and have a chat about all these interesting things. So I'm looking forward to it.
Yes, we are. We are looking. Yeah, we've talked about Drumlins, kind of alluding to Drumlins frequently throughout this, but say, well, we'll hold back. Won't dive into it too deep until we have the world's foremost expert on the panel with us. Hey, you're up there, man.
Okay.
Face it, you're up there.
Sounds good.
I bet you there's probably not more than 2 or 3 other thousand other. No, Drumlins are, I think what we should do is let Jerome kind of explain what a Drumlin is. We've talked about it a little bit already, of course, and how they might be connected with the deglaciation process and meltdowns and perhaps catastrophic flooding. But whatever the explanation turns out to be, I think it's going to be really interesting. And Jerome, like Brad said, was generous enough to spend 4 days with us up in British Columbia in 2017, getting instructed directly from somebody who's spent a lot of time in the field studying something that I think is going to turn out to be very relevant to understanding the past geological history of this planet. So Jerome, why don't you kind of maybe start by telling us your evolution into this subject matter and how you got interested in it, and tell us a little bit about your mentor, John Shaw, and then I'll talk about a little bit about that paper you guys came out with in 1999, Back to Brett's, and why I got so excited when I saw that paper.
Sure.
So if you don't mind, I'll just...
No, absolutely. So where to start? Well, I went to school in Montreal from back east originally. And at the time, at the end of my undergrad, I worked on a project that was trying to explain some interesting forms that are eroded in bedrock and that we seem to find mostly in glacial landscapes. There's some similarity or similar forms elsewhere, but in glacial landscape, they seem pretty unique. And so I came across some work that had been done by somebody named John Shaw and others. And then a few years later, I went to graduate school and worked with this person, and then continued graduate work after in Vancouver with one of John Shaw's former students, Tracy Brennan. And so they were both very instrumental in sort of developing some of the thinking, and then I don't want to call them stories, but the thought process that goes into interpreting some components of landscapes that have been affected by glaciation. And if you're a Canadian and you do anything related to earth science, you invariably encounter the effects of glaciation. It's a bit like if you come from the Midwest somewhere in the US, I mean, you likely live on glacial sediments, and the landscape around you is basically the former bed of a continental ice sheet. And so it's kind of, my interest in it stems from just really being outdoors and liking to understand how things operate. And there's a natural tendency to work on trying to, explain what's around you. And that happens to be glacial things. So it was a good match. And that I've never really sort of looked back since then in terms of the interest that related to glaciation and glacial processes and the sediments and the landforms that are produced. So that's what we're going to talk about today. I'm happy to sort of show you some of the broad strokes that are thinking about some of these landforms that we call drumlins and other landforms associated with them. So we'll start there, I guess.
I did want to add something. I recall that we got back in touch because you, like so many other people that were introduced to Randall, saw him on Joe Rogan.
Yeah.
And you got back in touch with me after seeing him on Joe Rogan. So
that's
that was
exactly
excellent.
it.
That was kind of the reconnection that you saw that also.
Yeah, I was watching an episode, and I think it's an episode where there was also Graham Hancock on it, and then they were chatting about scablands and British Columbia and floods out of British Columbia, and Randall was sort of mentioning all kinds of stuff. And as I listened to this, like, wait, that's what I worked on. So I thought, well, we might as well go have a look. And so then I think I found some email address, and it turned out to be you, Brad. And so then that's how we reconnected and ended up spending some time in looking at the actual landscape there. So
that's right. We actually got down into Washington a little ways.
That's right.
Probably what's behind Randall has just been on fire for the last week.
Absolutely. Yeah,
sadly.
That's exactly where it is. Right at the top of Omak Plateau.
On Omak.
Yeah.
Mm-hmm. Yep. I saw that too.
Yeah.
So, we can blame all this on Joe Rogan. So, like behind me is a picture of a rock drumlin that we visited up on the Omak Plateau. Let's see, I don't remember the order. I guess we could start by getting into, why don't we go back to the 2009 trip? You guys got anything to say on that? Or where were you in the 2009? Where did you guys go?
Oh, man.
Because John Shaw was on that trip, wasn't he?
No,
he wasn't.
No, he was at the conference. So with Jerome's colleague, Tracy, I did get a chance to meet John Shaw, however, briefly. But he was there at that 4-day conference that we went to after the field trip.
Oh, okay.
But it was primarily throughout the Scablands, Palouse Falls and Lataw Creek there, and Grand Coulee, obviously. It was 5 days, so we covered some territory. The outlet of Palouse River on the opposite side, where it confluences with the Snake River. I can't remember the name of the river coming in down there, but anyway, we hit a lot of spots.
Oh.
But it was led by Richard Waite primarily. The one I went on right after we met with Jerome in 2017, Vic Baker was on that one also. Richard Waite and Vic Baker were together on that one. Anyway, but what do you remember back then? That's 11 years ago, man.
Yeah, so it was sort of the major stops. It's sort of the classics of the Scablands. We started in Spokane, and then we went all the way to Portland, basically. So the full route through the Cheney-Palouse area, through the Columbia, the big coulees, Grand Coulee, Moses Coulee, Wallula Gap, slack water deposits in the Walla Walla Valley. And then there were a few other stops along the Columbia, around the Dalles and, towards Portland, because the trip was winding down in Portland. So, it was a good trip. And it was the first, I went in part because it was the first time that I was on a trip with Richard Waite, and who's, been pretty instrumental in writing a lot of the story of the Scablands. And some of the parts of it I don't always necessarily agree with. And so it was interesting to be in the field with him to sort of be able to chat. I mean, that's often some of the value of those types of trips, is you get into all kinds of interesting discussions with people, and you meet people like we met meeting Brad being the best example of that. But, you get to chat with people in a way that you don't usually chat at a conference, and you sort of you sort of think about, you kind of immerse yourself in that story for 4 days, and it's pretty fun. It's pretty intense. And if the crowd is good, if the other people are willing to sort of get on board, then you have all kinds of interesting discussions. And that was, there's long stretches of driving where there was a lot of interesting chatting going on in the van between the stops, and trying to
meals together and all that. Yeah. Plenty of time to chat. Yeah. There was probably 30 people. I mean, it was a full trip.
Yeah. So it was a good, it was a good trip and a good meeting. And
was that your first foray in depth across the Scablands, or had you already?
No, I had gone before. I mean, I think my first time through the first time through the Scablands, I drove through once, not fully appreciating why I was driving through it. And then years later, I was 98, I think 99, around that time, that was it was another one of those 4 or 5 days driving marathons that one actually started in Missoula, or even before Missoula, in the Flathead, right? So it's like.
All right. You mentioned that when we talked last week or 2 weeks ago, that was kind of the genesis of the paper that became the Back to Brett's paper.
That's right.
It was after that trip you took in 98. Right.
That's right. And then after that, I went back a number of times, not necessarily on field trips, sometimes just on my own with other colleagues, but not as part of an organized trip, but just to go back and do some of the work. And then the work in British Columbia that I worked on connects or is related, in some ways, to some of the Scablands. So that's an area that I've now gone back through a number of times in very, different locations. But it's a big area, if you've never been, it's a big area, and there's a lot of driving between stops, and there's a lot of open country. Central Washington is a lot of open country. So Well,
from the real big, you want to go back to start. So what's a drumlin?
Okay, let's start there. What's a drumlin? Well, the most simple way of describing it is to say a drumlin is a hill. It's an elongate hill that has a particular sort of morphology. I'm going to share my screen because I got a bunch of pictures, so maybe we'll do that way, and then that's probably
excellent.
I can talk around the pictures. So let me know if that works. And if it doesn't work, you good? If I do that, does that work?
Oh yeah.
Beautiful.
Okay. So these are examples of drumlins. These are from the Keewatin area of the Laurentide ice sheet. So they're basically in a very long, broad swath of land west of Hudson's Bay and east of Great Slave Lake. Okay, if you look at Google Earth, you can see that there's thousands of these hills. And the drumlin itself is this elongate hill. Okay. Now, if you look through all the literature that you might find, and even in textbooks, they'll tell you that a drumlin is like an inverted egg or inverted half egg, or it's like the back of a spoon, and that kind of descriptive words to explain them. But fundamentally, it's a hill. It's elongate, meaning that it's not, it's got a long axis and it's got a much shorter transverse sort of axis to it. You can see that there's a ridge that defines the drumlin. And then many drumlins, not all of them, are not fully symmetrical. So sometimes you get perfect symmetry in the hill. Other times there's one side of the drumlin that's steeper than the other. More often than not, and certainly if you read books, they'll tell you that the side that is what we call the Stoss side tends to be steeper. And then it tapers down a gentler slope on the backside. But in reality, recently some people have done some work using digital terrain models, and really you get everything. You get fully symmetrical ones. You get some that are asymmetric that sort of have a steep side on one end, and other times the steep side's on the other end. So we don't have to get hung up exactly on the morphology, but the idea is that it's this elongate hill. And the other way that I think you have to think about drumlins is that they occur in groups. So it kind of sounds funny when you say, look, what's a drumlin, and you describe it as an elongate hill, but part of the way that you recognize drumlins is that it tends to happen in big groups. Okay, so it's related to other forms that are similar. There's these big clusters of drumlins, hundreds to thousands, if not tens of thousands of them that you find together. So part of your ability to recognize a drumlin is probably also related to the fact that it's next to very similar hills of similar shape and similar orientation. That makes sense?
Mm-hmm.
Yes.
So once you sort of go,
that the Stoss side is generally going to be the up, whether it's glacier flow or water flow or a combination that has ultimately sculpted the drumlins, the tapered end is usually going to be downstream.
Yeah,
right?
exactly.
Stoss cell, which is the upstream side.
Right. And so what you're getting into is kind of what do we use drumlins for, right? I mean, what do they tell us? And what we use them for, if you think of it from the standpoint of producing maps and trying to understand former ice sheets, is that people will use drumlins as indicators of flow. Okay, and I'll keep it at flow, not necessarily, in the minds of many, it's ice flow. And in some cases, as we'll discuss later, it could be representing water flow underneath the glacier. But the idea is that the elongation is sort of pointing in the direction of flow. Okay. And in the case where you have drumlins that aren't perfectly symmetrical, we call the Stoss side, or the side of the drumlin that you could call the upflow side, the one pointing into the flow, whatever the flow is, that's the Stoss side, and that's the one that's going to be steeper. Okay, so the asymmetry puts the steep side facing into the flow. Now, if you map enough drumlins, and I'll show you some other examples in a second, you realize that they have enormous variability in their morphology. So here's another example. This is from a terrain model, a DEM. You get the idea of elongation, right? You can see sort of, it kind of looks like streaks on the landscape, but each one of these ridges here represents one of these drumlins, and you realize quickly that they're grouped, right? I mean, you can't just look at this landscape and miss the fact that they're actually just completely grouped, and that there's these very close relationships between the forms. Sure, they vary in shape and they vary in length and everything, but fundamentally, there's just a cluster of these forms together. More examples. This is from Wisconsin, Green Bay Lobe, I think. And it's really just to show you, so the color image is just a portion of this gray one. You can see on this gray map, this is the moraine that marks the margin of the lobe. So you get a picture that basically ice was flowing from the top of the picture to the bottom. The white line here, the Johnstown moraine, marks the furthest extent of that lobe of ice. And what you're seeing to the top of this picture, so basically underneath the lobe and upflow of the lobe, is the bed of the ice sheet, the former bed of the ice sheet, which is the modern landscape today. But of note are all these little elongate hills, which are all the drumlins. So there's a 20-kilometer scale bar. We're probably looking at, like 40 miles across the entire picture. And just looking at the number, you realize there's dozens, if not hundreds, of these drumlins that cover the entirety, or almost the entirety, of this lobe, the footprint of the lobe. And if you zoom into a portion of that, the drumlins look like these. And so within even just that little area, there's lots of variability in terms of the shapes. There's some really long and skinny ones, and there are some shorter, stubbier ones, but they all have this elongation. Okay, so if we're going to define a drumlin, elongated hill, but really occurring in a cluster of others of similar hills.
So looking at that map in the top left, you got the little inset showing the Laurentide ice sheet, and then the block that's expanded. So it's far southeastern Wisconsin. So basically, those are just north of Chicago.
Yep, exactly.
I'm guessing most people in Chicago have no idea that the landscape looks like that just outside the city, or the story behind them. But yeah, I'm glad we had a little scale on that one, the 20 kilometers, because the previous one I was wondering how long some of those forms were.
Yeah, the thing is that given the canopy of trees and vegetation, they're not readily apparent from the ground.
That's right. Or there's
in some cases they would be, but out in an open plowed field or something. But
I mean, like everything in geology, the scale is important, right? So if you look at just this image, you can see that individual drumlins are often, 2, 3, maybe even 4 kilometers long. So it would take you a while to walk the length of one single drumlin.
Right.
And if you climb on them, again, the height of the drumlins varies depending where you find them. It's a variable quantity there. So they can be a few meters in height, sometimes tens of meters. And in the biggest cases, they could be close to 100 meters or more in height. So there's quite a bit of variability in terms of the morphology, but you recognize them in part because of this elongation and some of the patterns and the groupings. And of course, to make it a drumlin, it has to be something glacial. So it has to be within the footprint of a former ice sheet or glacier. So no drumlins in Texas. Or,
That's the point Randall made last week, that you never find them outside where there was an ice sheet. They were always under the glacier.
That's right.
Yeah.
Now, I noticed there on the broader view how they seem to essentially be splayed outwards.
Yeah, on this lobe they are, exactly. So you can see if you look at the patterns, and I'll show you a map of what we'd call flow lines. So if you sort of group and you map enough drumlins, you start seeing regional patterns in the direction that they're following or their orientation. And so you start seeing exactly that, some splaying here. So for example, if I use my cursor, these sort of kind of curve and go in this direction while these curve and go in the opposite direction. So they kind of have this display pattern. So we were just saying before that, so what do you use drumlins for? Why are they so interesting and mysterious? Part of the reason is because we use them to map, and they're really integral to the reconstruction of an ice sheet and understanding how big it was and the direction of flow. And if you're going to map ice sheets and glaciers, you kind of use moraines as best you can to sort of mark the furthest extent of the ice sheet. But that kind of puts a line on the map in terms of the ice probably, didn't go further than this line, this point. But if you cover a continent or the better part of North America or in Canada and the northern US in ice, that ice was following different directions. It was moving in different directions. It's not a uniform flow path across the entire landscape. So the drumlins become landforms that are potentially useful in trying to understand the path of the flow, essentially. And so if you start mapping enough drumlins, you can start seeing what we would call flow lines and flow tracks. And so this is a map that was actually made by John Shaw a few years ago. And the thing to notice here is that the blue lines are generalized flow lines. And so it means that, you imagine that you map enough drumlins and you'd see a regional pattern and continuity between the drumlins, and you can sort of start tracing pathways. And groupings of these flow lines will define the broad yellow zone, which are zones that are what in this case were called flow tracks. So just call them, groups of flow lines. But what you see is that the patterns of drumlins records, very variable directions of flow. You've got some in the north that are heading in the north part of Canada to west of Hudson's Bay that are heading almost due north to the Arctic. Others are heading due west. Some are going to the south towards the Dakotas and eastern Montana. We were looking at that previous image where we're down in the Midwest and the Great Lakes area. There's flow lines that go towards the margin there. What you're seeing over Quebec and Labrador are its own little system of flow lines. And so it's reflecting the fact that the Laurentide ice sheet grew and developed and built up essentially a number of spreading centers. The ice was emanating from multiple locations, and it had what we call ice divides. So there's a point where ice is moving in one direction, and past that point it's moving in the other direction, much like you have a divide in a watershed where rain on the landscape flows into one basin versus another. You can think of it that way a bit with ice. And so these flow lines help us sort of picture the patterns of ice flow and potentially, as we'll discuss, meltwater flow that might be present. So the drumlins are really, really central to making sense of glacial pattern and dispersal patterns. Now, one of the interesting and at the same time perplexing things about drumlins is that every ice sheet, active or paleo ice sheet, former ice sheet, those that disappeared after the last ice age, has drumlins on its bed. Some glaciers some smaller glaciers also seem to have landforms that resemble drumlins. People have been identifying drumlins and thinking about their genesis, how they formed for centuries, and we're not really at a point of consensus on how they form. Okay, so this is something that people have been mulling over, trying to understand, and come up with with some explanation as to how they form. And we haven't arrived at sort of an explanation that sort of satisfies all the observations that we tend to see, and that can be kind of unequivocally stated as being, this is how drumlins form. Okay, we're not there, despite centuries of people looking at these forms and trying to understand what they are and how they're created. So they're enigmatic that way, right? There's a lot of questions that trying to understand drumlins triggers in terms of how we think ice sheets work and how the bed of an ice sheet operates and what's the role of water versus, large amounts of water or small amounts of water or no water at all. And
while you've got that map up there, Jerome, well, I just wanted you to point out the Great Slave Lake and then where that field is from that first picture you showed. And, that's probably hundreds of square miles or more probably out there, isn't it?
Yeah, so that first photo was taken out of a helicopter, and it's in this area here. It's within this big flow track right there, okay?
Right.
It's one drumlin amongst many thousands that makes up these probably 8 or 10 flow lines as part of this flow track. Okay, that's sort of I'm on the wrong lake here. Sorry, Great Slave, right here, in this area, just below it.
Okay,
one of many flow tracks.
The other one's Bear Lake. Yeah,
Bear Lake, Great Bear, my bad.
Right, yep.
Yeah, this is the east arm of Great Slave Lake right here, and that's the flow track is right in here. This is where the cursor is. All right, so let's get right into it because I know that Randall was interested in this discussion about this idea. So in the process of trying to understand drumlins in the early 80s, John Shaw and some of his colleagues propose a model that involves essentially very, very large floods of water under the ice to create drumlins. Okay, it's happening at a time when other ideas already exist in terms of explaining how drumlins might be created. It involves mostly at the time the idea that the bed of glaciers deforms. So if you may have talked about glacial materials like till and things like that in your show before, but the sediment that's produced by the abrasion and the breakdown of rocks on the bed of glaciers produces this really, really poorly sorted mixture. So it's got every grain size. It's got clays, silt, sand, gravel, big boulders. And this is what's basically a layer of sediment that's on the bed of glaciers. And it's produced both by abrasion and the breakdown of rocks, but also there's a bit of transport of the material underneath the glacier. And the transport is often facilitated by the fact that you can deform that sediment when it gets saturated with water. So it's not dry sand, gravel, and clay. It's actually often quite wet, and it can be fully saturated in water. And that layer of sediment deforms. It accommodates some of the movement of the glacier. So the glacier is not just sliding on bedrock or sliding on some of that material. It can actually also move because the sediment itself is moving. And at the time, in the 70s and 80s and even before, people had clearly an inkling that the till was an important component to understanding the formation of drumlins, because many drumlins are composed of till, but some drumlins are also composed of other materials that's not till, which becomes problematic because you think, well, if you think that the drumlin is forming because till is deforming and it kind of builds up a hill of till, then how do we explain those that aren't made of till? Or how do we explain those that are just made of rock? Because sometimes you see that drumlins are made of rock only. So there is, again, I said, it's been centuries since people have been looking at drumlins, and there's no real consensus on their origins. So this was one of those cases where there were some open questions. There were some issues in terms of being able to have a hypothesis that explains the range of observations. And so an alternative hypothesis proposed by Shaw at the time is that drumlins actually are formed by water flowing underneath large ice sheets. And when I'm saying that, it means, vast quantities of water. We'll get there in a second, but vast quantities of water, enormous amounts, basically mega flood scale amounts of water that are moving underneath the glacier. Okay, so I wanted to put that up front just to give you a visual of what this idea entails, but then I'll sort of walk you through the steps of how we get there to understand what the evidence is that's been used to support this model. But if we explain this diagram real quick, picture that you have bedrock on the bed of a glacier. You've got some amount of sediment, and you've got a series of landforms that are produced, and they include drumlins, as we've been talking about. There's some till here. We call this lodgement till. That's one of the types of till. We've got drumlins. We've got other forms that we call rogans, rogan moraines. Same idea, same landform, slightly different terminology. And the idea here is that what we've done is just lift up the lid of ice. So this is the ice sheet, just a cutaway of the ice sheet. and we're sort of hinging it up so we can expose the bed. And then there's this sheet of water that flows across the landscape, and it's that sheet of water that does essentially the bulk of the work in terms of creating the landforms that are then found on the bed of the glacier. So in this model, it's not the direct interaction of the substrate and the ice that produces the landforms. It's actually the passage of this sheet of water underneath the glacier that can either erode or, as we'll see in a second, create spaces for deposition of sediment that will then become drumlins. Does that kind of make some sense? I'm not sure if, I'm not sure if the visual is clear, but that's
No,
we're going.
that makes perfect sense. That's great.
That was good.
So, one of the issues with drumlins and why it's taken centuries to figure out, and maybe you could argue we haven't quite gotten there yet, how they form, is that, it's really tough to study ice sheets. Because if you study ice sheets after they're gone, obviously you don't really know what they're doing at the time of drumlin formation. You're always sort of working backwards from the evidence that you see in the field. So you got to work from basically the sedimentary and landform record, and you have to sort of work backwards to try to understand the process out of what you can understand from the deposits. Or you could go to a modern ice sheet, because we said that, it seems like every major ice sheet seems to be forming landforms like drumlins. But obviously it's under an ice sheet, right? And accessing the bed of an ice sheet is pretty complicated. So that's a real hurdle to making, progress that way, because it's very, very tricky in terms of getting data, whether you're looking at the former drumlins and the former bed of an ice sheet, or if you're looking at an active ice sheet, say in Antarctica. So you have to use other methods, other tools like geophysical tools that give you it's kind of a type of remote sensing to try to understand something about the bed of the glacier and that's active and how it might be moving sediment and how it might be shaping its bed into particular landforms. You can look at areas that have been recently deglaciated, but obviously, again, you're not really observing it directly. So you're kind of always playing catch up in terms of the process. You're not observing it as it's forming in the moment. It's not like if you're studying a river where you can actually stick instruments very easily into a river and measure the speed of the flow and the movement of sediment, right? So there's a hurdle there that is just, you can't really get around the fact that those areas are environments that are very hard to access.
It's the measurement problem of drumlin mechanics.
Yeah, that's right. Exactly.
So you have to proceed in a lot of cases by analogy.
Exactly. That's good. Yeah, thank you. Absolutely. Analogy is key. And in fact, analogy was not exclusively, but in large part, the basis for this picture, this model that I'm going to try to explain to you, which is what John Chaw proposed. So let's start small scale and we'll go up, but you'll see why, because the analogy connection is pretty poignant with these next few slides. So in glaciated landscapes, there are many outcrops in glaciated landscapes that have really beautiful, spectacular marks of erosion. In other words, the bedrock has been eroded into very intricate shapes and forms. This is one example of an outcrop of marble just north of Ottawa. And I'll just point out there that this is an elongate outcrop, but on that surface, you'll see all kinds of elongate, sort of high-standing parts surrounded by depressions. There's a depression wrapping around the front and extends to the sides. We call these rat tails. This is a term that, we give names to things in various scientific disciplines. So this is commonly called a rat tail, but really what you should see there is a residual, right? There's rock that's been removed, and the rock has been preferentially removed around the sides and around the front of it, which leaves behind a residual and leaves behind some amount of rock that's shaped as a function of what's been removed around the flanks and the front of it. And there's a big one there. There's a couple of small ones over here. There's a series of other small ones there. And if you get in a bit closer, you'll see that they occur at multiple scales. So there's a small one here. There's another one here that you can see the furrow on the edge of it, and it wraps around the front. So on this picture, as on the one that comes after, the flow is from right of the picture to the left. It's the same idea here. The flow is from the right of the picture to the left. What you might notice on here is that the surface is full of kind of scratches. And these are what we call striations or striae. And they're pretty diagnostic. In fact, not too many people argue about striations. That's probably the best piece of evidence you have for abrasion by a glacier. In other words, if you think of a glacier, the base of a glacier that's charged with all kinds of pieces of rock and other sediment, as a great big piece of sandpaper that's sliding over a bedrock surface, it's going to abrade it. It scratches it and it breaks down the rock. And at the same time as it does it, it smooths it and polishes it a bit. But fundamentally, it scratches and it breaks it down sort of grain by grain as the rocks interact with the surface. And so you produce these striations, and they're very diagnostic of glaciation because they occur all over glaciated bedrock surfaces. So these particular forms have striations, which we might be taking on as examples of or evidence of abrasion, but they also have these really intricate sort of kind of sculpted components to them, these little furrows and the wraparound parts that leave behind the residuals. If you look at other examples of them, you can see them on other bedrock surfaces. All these are from examples of glaciated areas, but you can see it really well. In this case, the flow is from the bottom to the top on this picture, and there's a very hard little piece of chert, which is a silica-rich sedimentary rock that's quite hard. So it resists erosion and abrasion a bit better than other surrounding rocks, and it's an inclusion there, a little nodule. And what you've done is you've stripped away material around the nodule to produce this really nicely curved or horseshoe-shaped little trough or a little moat, this what's called here a crescentic scour, and then it extends laterally continuously to the furrow, which leaves behind the residual. And you have it there, you have it here, same idea, flow from bottom to top. Here the flow is from right to left. But this is a pattern that we see frequently on bedrock surfaces that have been under a glacier.
Can I quick?
Please.
On B,
yeah.
We are looking at a form that was that produced, that's plaster, right? With a chert nodule. Is that correct? Is that
no, that one is actually bedrock.
No, that's actually bedrock.
Yeah. What you're thinking about is this.
That's what I was thinking of.
Okay.
Yeah.
So in the attempts to explain how these forms are produced, whatever size they are, you got some here on the bottom on D that are really small, a few centimeters. In other cases, the previous photo, you can see that they can be very, many meters in length. Irrespective of the actual size of it, you try to explain these, and you face a bit of a conundrum because there's components of those forms that are probably best explained by erosion by water. The fact that you have this crescentic scour here is pretty diagnostic, I think, and I'll show you some of the other evidence for it in a second, but pretty diagnostic of what you have when a turbulent fluid encounters an obstacle and has to flow or split around that obstacle. It's called flow separation. You get initiation of a vortex, a turbulent structure that splits around and essentially is capable of excavating and eroding around, that splits around the nodule or any obstacle, is capable of excavating the material preferentially there as well as along the flanks. I would argue, and I think some people would disagree, but I would argue that that sort of feature is not something you produce easily when it's only ice moving over a surface. Ice is far too viscous to be turbulent at that scale, and it's therefore not able to preferentially remove material at the front of this obstacle and along the flanks. Okay, so if you have a glacier moving and encountering an obstacle on its bed, like a big bump, it's going to have to flow around it. There's no question about that. But it will not preferentially excavate around the front of this obstacle, in large part because this form that leaves behind really, really sharp ridges or sharp rims around the part that's excavated, that is not something you expect out of glacial abrasion. Abrasion tends to plane things off, right? It makes things smoother. It doesn't preferentially strip away material in one location versus another. Okay, that's one of the biggest, I think, pieces of evidence that supports the idea that some of the glacial forms we see on the landscape have had the influence or have been formed either entirely or in large part by water, turbulent water. Now, how do we arrive at this conclusion, or how can I make this statement? Well, you can run experiments, and that's one of the ways you try to figure out how enigmatic landforms like drumlins might actually be created, because you can't really get on the bed of the active ice sheet. And if you're dealing with a landscape, well, you obviously don't see what's going on. So you run some experiments. There's a whole side of experimentation that's really useful. So Randall was asking about plaster of Paris. So this is an example of this. This is the white parts that you see there are plaster, fine grain plaster of Paris. And inside the plaster of Paris are some little chunks of little cubes. I think they're cubes of pyrite or something like that, or something more resistant. And then they're put in a flume where you run water over them. And the obstacles trigger the formation of vortices. And those vortices, then this turbulent structure that's this vortex is able to selectively, if you want, erode and remove material in specific locations. And so specifically where you see it being removed is right around the obstacles themselves. We start seeing similar forms. This is the idea of the analogy, right? We start seeing, this form looks very much like the form we see on that outcrop north of Ottawa or other outcrops elsewhere. But here we've got a pretty good idea of what's going on. We have a pretty good control on the conditions where it forms, the fluid that's moving over it. And so this is probably one of the better examples, but here's a little residual ridge that you have here, and you can clearly see the moat around it that stretches laterally. So this ridge exists only, and we see it only because we've been able to strip away selectively the plaster of Paris around this area, right? So that's a low or negative part or a negative form, and this is a residual high point. Does that make sense? Is the visual kind of clear that way? So if we go back this way, we see, hey, look, there's an obstacle, there's a residual high, and there's a moat. So a negative form, stretching, wrapping around the front, stretching along the flanks, this furrow and scour combo that leaves behind this residual. Well, and there's the same thing here. There's a tiny one and more moats and furrows. Yeah, Brad.
Well, I was just going to point out, if people haven't picked up on it, you've got some items there for scale. You've got a coin in the lower left on C, and then there's the camera lens cover on B there. So just so people see that, we're at a much smaller scale, but it's pretty much identical forms that we're seeing on a wide range of, scales. So that's one of my roles, scale man, point out scale differences.
Yeah, it's a good point, but in a way, the scale doesn't matter.
Right.
This is one of the incredible things about all this is that I'll show you some pictures in a second of drumlins that are kilometers long, but the form is identical.
Exactly.
So if you don't know the scale, you might not be able to tell whether it's 15 centimeters long or 1.5 kilometers long, but the form is so diagnostic, and you recognize so many of those critical components of the form that the process that might be responsible for creating that becomes essentially obvious or becomes self-evident just because of such a strong similarity of form and the analogy between the two.
What makes analogy, I think, such a powerful tool is the scale invariant nature of this phenomena. And I think you cited in the recent paper 7 orders of magnitude.
Yeah.
Spanned. That's pretty amazing, really.
Yeah.
Yeah.
Yeah, it's quite incredible. Are we good? Still good?
Oh, yeah.
Moving along? Perfect. All right, so we're talking scale. Let's bump up scale.
Yeah,
so
let's do.
So we've got these plaster of Paris little obstacles. In this case, it's a few centimeters across the entire picture. But now we're moving into something that's, I think, something along the lines of 400 meters across the entire picture. Okay, so bottom left to top right. We've now jumped up a few orders. This is in the French River area of Ontario. It's a bedrock escarpment. And so it's like a step made of rock, but that step was facing into the flow of both ice and, in this case, in water. And it's been sculpted. It's been eroded selectively. And we start recognizing exactly the same forms that we were just seeing very small before and somewhere in between the two scales for the outcrop north of Ottawa. But let me point out to you the important parts that you need to be able to recognize to see the forms. If you think of the moat and the lateral furrows, often those little moats, because they're negatives or depressions, they fill up with water. So every one of these little black spots or dark spot is a bit of a puddle of water. And it's there because it occupies one of these crescentic troughs that extends laterally. So you can see there's a good example here. There's a crescentic one that moves laterally to this one. There's a portion of one here. There's another one here, and the furrows extend laterally. There's more over here. So you see, for example, that the erosion is obviously most prominent around the nose of the form on the front of it. and it tapers a bit downslope. So as you proceed, so the flow would have been from bottom right to top left here. So as you proceed along the flanks of it, the furrows peter out; they sort of disappear a bit. So the lakes are preferentially formed at the nose of the form because that's where you have the deepest scour and depression.
Mm-hmm. Then I think you used the term shoulders.
Yeah, exactly.
You have the neck, you have the nose, and you have the shoulders.
Okay, we can go that way if you want.
I like that.
Okay, or we can go front, or we can go stoss, and we can go on the flanks. Whatever works.
It all works for me.
A couple other examples, because I actually just think those forms are beautiful, regardless of how they form. They're just striking.
Oh, yeah.
Like the sculpting is really something that's incredible. So this is from a place called Kelly's Island in Lake Erie in Ohio. There's a very prominent, it's an actual state park, I think, where you can go and visit. But there's a prominent channel, basically, cut in limestone. And the inside of this channel is entirely sculpted with these forms. So it'll give you an appreciation for the range of forms and how they might organize themselves together. There are some examples there. I was talking earlier about kind of this conundrum between what abrasion by ice does and what water erosion does. And this is a good illustration of that. You can see here, so what we're looking at here are these very intricate sort of curved erosional depressions that are in the bedrock and the limestone, but within those depressions, all these little remnant, very delicate little rims and ridges inside. These are not features that we necessarily expect to be preserved as ice potentially abrades this. What it would tend to do is actually attack and wear down these rims preferentially. They're sticking out the most, and they would undergo the most amount of abrasion early on, and they would tend to wear away so that we wouldn't preserve them. So the fact that they're preserved there is potentially a very good piece of evidence to argue that it's not in fact ice that abrades these forms into that shape, but it's really water that produces the key part of the erosion that leaves these residuals.
So it's definitely not a product of the rock itself then? Like that some of those areas are just much tougher? Is that part of it?
Yeah, that's a really good question. So in some cases, there is something going on with the rock itself. So I'll go back a few slides, like this one here. That outcrop near Ottawa has inclusions of rocks that are much harder. And we do see that preferentially, those seem to be the points where the vortex starts to occur, right? That's where it initiates.
Yep.
So having an inclusion or something harder, an obstacle, something that essentially creates a perturbation in the flow might be the point where you start the process, right?
Okay.
But then the rock around it, in this case it's marble, is softer than this inclusion, and so we excavate more just because the rock is softer, and so we preserve this inclusion. So the inclusion is both an initiation point, but it survives longer in that sense, right?
Right.
But you can absolutely start those forms without having an inclusion necessarily. It's not an absolute requirement, but it certainly helps the process if you do. Okay, so let's get to the pictures of this is inside this channel at Kelly's Island, and there was an interesting paper written about these forms that maps those crescentic scours and the extent of the furrows. And so you really get the idea of how many of these forms are superimposed within this conduit. So there's a lot of very delicate forms that are preserved and that are present within this conduit. So it's a channel that the interpretation certainly is that it was conveying lots of water that was flowing turbulently, and within that turbulent flow were these coherent turbulent structures that were preferentially excavating these troughs and leaving behind these residuals inside. So it's essentially erosion by a turbulent fluid. And you were asking about the rock itself, but really you have to picture that it's not just pure clean water. More than likely, it's water that's carrying lots of fine sediment in it. And that sediment is also able to do some work in terms of, excavating and eroding and abrading, because it's kind of like a wet sanding effect, but but mostly driven by the turbulence in the water. There's some details of those surfaces inside the conduit. So you start recognizing there's lots of similarities between these Ohio forms and those that I showed you from French River in Ontario. The scale's a bit different. These are a little bit smaller. But again, if you don't get hung up on the fact that they have to be the same size, which they don't, you start seeing the same shape or the same form irrespective of scale. Right?
Yeah, that's amazing.
And as you see, they're beautiful, right? They're just,
yeah.
It's,
that's what I was going to say. It's quite beautiful, yeah.
Yeah, I mean, the sculpting is just, I don't know. It's one of the things, you're asking how did I get into this field? Because I went to that outcrop near Ottawa as an undergrad and I saw those forms and I thought, wow, that's just interesting, period, because it's beautiful.
It's beautiful. And yet the fact that it's diagnostic and you can look at this thing and it's indication of paleocurrent direction.
Yeah.
To me, it's just like, it's telling you this story and you go clearly, there was a phenomena that happened here. Whatever the exact nature of this sculpting was, it was something, and it was a very interesting process.
Yeah. Yeah. So, I mean, since we're on the topic of sculpting, what's really key here is if somebody could make the counter argument and say, well, I could totally picture how a really big boulder frozen to the base of the glacier moves over this surface and kind of gouges out this channel here. And if you think about that happening, what you'd expect to see is a very rough resulting kind of gouge.
Yeah.
You would not expect to see something so smooth. And so you with these forms, you have both the component of having smoothed the surface, yet having had the ability to preserve really, really delicate features that are part of that smooth, delicate form, right? The full feature. So ice is really, it's difficult to do it with ice that way. You kind of have to pick and choose. If you want a boulder to gouge out the form, it's not going to be smooth. If you want the surface to be smooth because you abrade it, it's not going to preserve delicate features, right?
Right.
And so with water erosion, you have a mechanism that can both produce a smooth surface. And it's smooth in part because that water that's turbulent is carrying some sedimentary particles that do some amount of abrasion. But the pattern where the abrasion happened is dictated by a larger turbulent structure in the fluid itself. Okay?
Right.
Does that make sense?
Yes.
Now, where is this relative to the southern margin of the whatever lobe this was in Ohio?
We're in Lake Erie.
Okay.
Near the southern shore of Lake Erie, and so it's like northern Ohio, right?
Uh-huh.
So we're not that far from the margin, but we're not right at the margin.
Gotcha. Which is pretty typical for drumlin swarms.
Yeah, they occur all over. I mean, it's not, they're not specifically indicative of margins necessarily.
But we don't find them beyond the margins. That, I think, is a key
That's key, exactly.
So last week we started talking about potholes, and Randall was describing the vertical drilling. So now you pulled it up here. What I was about to say, you've got this kind of corkscrewing water movement, like a horizontal tornado instead of these vertical tornadoes like we were talking about last week. So we need to take a break up here sometime. Is this kind of a good place, or can we get through this one in a few minutes, or you got kind of a break point?
No, we can stop here if you want, or if you give me two minutes, we can just sort of wrap this one up with the pictures, and then we'll take a pause on that.
Okay, yeah, a couple minutes, 5 minutes is fine.
So we've kind of been dancing around this picture without showing it, but there it is, right? There's a schematic of what we're talking about in terms of being able to have a flow of this turbulent fluid, in this case, it'd be water, and it produces this turbulent structure, this horseshoe vortex, as it's known. So you have these counter-rotating vortices that you can see them on either side that split off from the flow that has to flow around an obstacle, just like we saw in the plaster of Paris. And this is what's doing the work, right? This is actually what's excavating. And so that vortex is carrying some sediment. It's abrading, so it produces a relatively smooth surface along the stoss side and then along the flanks. But it's also producing these really, really sharp rims in the bedrock. So you kind of get the combo of those two parts. And importantly, it leaves behind a residual, right? It leaves behind something that ends up being the rat tail, or might be the drumlin if it's large enough, as we'll chat about in a few minutes. But the residual is the form that you see, but it's integrally defined by the fact that the form itself is really dictated by these areas where you stripped away material. And this is not a complicated diagram, and it's not an esoteric concept that flow, like turbulent fluid, splits around an obstacle. Engineers know this problem forever with bridge piers, and there's, excavation around the foot of bridge piers, especially when the flow, during floods. It's a real engineering issue because you get exactly the same structure developing in one of these bridge abutments or these piers on the bridge, and it strips away all the material that you've anchored your bridge into. So it's a real issue, but this is not, something that is particularly controversial in and of itself, because the form itself and the turbulent structure, it's all over the hydraulic engineering literature. Nobody would bat an eye at this diagram. And there's a computer simulation of it. If, some people only believe it if a computer spits it out. So there it is. I'm just being a little flippant, but you get this is kind of an interesting visual, because you really see the different patterns of turbulence that are produced. This is the engineering example. Imagine this is your bridge pier, and you can predict where you're going to have preferential excavation and erosion, where you're going to have your problems where materials being stripped away. Where this becomes a bit more controversial is the argument that this happens in enormous flows of water underneath a continental ice sheet. Okay, that's where we'll see the sticking point tends to be. But in and of itself, we call this a form-process relationship. There's a form and there's a process to explain it. It's very strong, right? There's that linkage between what you see as a form or the product and then what creates it. It's a pretty solid argument in terms of why you might produce a residual and preferential excavation. Why don't we stop there?
All right.
For now, before we move to Drumlins.
Yeah, fantastic.
Can do.
Fascinating stuff, man. Thank you so much.
Yeah.
Welcome back, ladies and gentlemen, to Cosmographia, the Randall Carlson podcast. And before we get into Drumlins, if you are stuck up all night because you can't sleep and you're watching Kosmographia videos, that's great. But maybe you should try some CBD oil from cbdfromthegods.com. Randall seems to be having good results. So
Indeed.
check it out.
Indeed. And I'm quite excited at this moment. Not only because we're talking about Drumlins, one of my favorite all-time things, but also because this came today. My new shipment. So I'm good, man. I'm good for the next month.
Yep.
So,
and if you visit cbdfromthegods.com and you order something, put in RC ships free, and you will receive free shipping. So
that's right.
Yeah, man.
That's the cube of cures, huh?
Yeah.
Yes, the cube of cures. Yes. Yeah, I haven't even opened it yet. I'm gonna, it's gonna be a ceremonial opening when I'm ready. I've still got my previous supply, which I'm down to a couple of days left. But I will say that since I took that tumble a week ago Wednesday, I've doubled up the dosage, so it's actually going a little faster than it would have. But today, I can say I'm getting around pretty good without hobbling, and I'm finding the salve really seems to be doing something beneficial, because I'm doing internal and external. So, I was in say maybe next week, if it's if people watching can stomach, I will show a picture of the bruise on my leg. It's very impressive. You'll be impressed when you see it.
Is it a streamlined form?
Streamlined erosional?
No,
residual?
it's just a big blunt. What's the term, Jerome? This is one of the things that I'm not going to let you get away from here tonight until you've told me how to pronounce musselbrush.
The Musselbrush?
So okay, wait, Musselbrush.
Yeah, Musselbrush. Like you have the word muscle in there, so think.
I had
muscle.
it. Yeah. Okay, Musselbrush. Yeah.
Yeah.
That's what it looked like.
Yes.
Okay, so we'll be getting that. I'm sure we'll be talking about that at some point. So we can bring this up because this is another good example of analogy. So,
well, last week we had moose drool. This week we got Musselbrush.
You had moose drool last week? Is it like the beer? You had the beer?
Right. We were talking about it last week. Yeah. Yeah. So as always, the links, the RC ships free, all that stuff is in the description, show notes. So check it out there. You can link directly into cbdfromthegods.com.
And let us know. Let us know what happens if you've got it for a particular issue. And at some point, we should maybe get Mike Robertson on here to talk about the endocannabinoid system, because that is some really interesting stuff to learn about.
I have seen people have been emailing Kosmographia and saying that they've gotten it and have had good results.
Really.
So, yeah.
Well, anything that will help us live a couple of extra decades, because we've just got too doggone much geology to study.
Yeah. There's a lot of geology we got to get to.
Yeah, we're going to need those extra decades of life. So anything. All right, let's get back to Jerome and Drumlins. I am just really eating this up. I love it.
Riveted. Love it.
Yes.
Okay, so before we were looking at this just example of the horseshoe vortex and the fact that we're saying it's not a particularly controversial idea that that form is produced in water. But where we're going to go next, I'll sort of walk you through as we step up in scale. What also happens is that this idea of meltwater, those quantities of meltwater producing those kinds of landforms, and including drumlins as we move beyond this, this is not mainstream idea. They're not widely accepted idea. Like this meltwater hypothesis of Shaw has always been and continues to be a fairly contentious issue and controversial. And so I don't want to give people the wrong impression that this is sort of a settled argument at all. It's far from that.
Right.
I want to go through some of the arguments that have been used to support this idea and to build it from the beginning. But the more we move into the next few slides, the more controversial it becomes. I don't think that many people argue the fact that these bedrock eroded forms are not a product of water in large part, though there's obviously evidence of abrasion by ice as well. But as we start scaling up the size of drumlins, what also happens is the amount of water that is required also increases radically. And this is where the idea becomes increasingly controversial. Okay, so we can sort of chat about how that gets to be that way, but I'll tell you right now, that's where we're going. So more examples of what happens when, for example, you have a flow that encounters an obstacle. We're talking about these French River forms being at escarpment. So you can see, I think my cursor shows up, there's a positive step here. We basically go from a low-lying area up a step, and then there's a platform surface that's sculpted on the bedrock. And so you have to picture that as the flow was going from the bottom right to the top left, it's impinging or it's encountering an obstacle, a positive step, as we call it. So there's like a bit of think of a staircase, and there's one step in the way, and then you get onto that flat surface. And so if you model this, computer models or hydraulic modeling of flows encountering what we call a positive steps, here's the best way to think about it. There's our bedrock surface, and then there's the low-lying area upflow. We encounter the step, and we go over it. What we're able to see are patterns of turbulence, and in this case, patterns of erosion that might be produced that are entirely compatible with the patterns that we see in the bedrock. In other words, what we see is you encounter a step. It doesn't stop the flow. It actually, what we start seeing is a lot of turbulence at the bottom of the step, but also the tendency for the flow to overcome the step and stream across the top, right? So the flow gets focused along the top in these streamlines across the obstacle, and those happen to correspond also to the general elongation of the erosion along the flanks of the bedrock residual. So there's this aspect of erosion to produce individual forms, but if you start thinking about groupings of forms that occur on positive bedrock steps, that's also consistent. The pattern we're seeing is also consistent with what we understand of how fluids move over these steps. Okay, so the modeling in this case was done in part to try to understand, hey, what does happen when this flow of water into the ice might encounter a step, and then it produces patterns that are certainly compatible with what we're seeing in the bedrock. This suite of forms that we see in bedrock, whether it's the one on the bottom right, which is Kelly's Island, or this is from French River area. In the 90s, one of John's, I think, colleagues, and John as well, John Shaw's colleague, mapped a range of these forms, and they kind of produced this atlas. And they said, hey, there's actually a whole collection of these patterns of bedrock erosion that are produced by water. And so they tried to sort of create this nomenclature of them. Some you'll know, right? So potholes, you know what potholes are. We see these in rivers, but we also see them clearly in those areas that have been glaciated in combination with the ones that tend to be horseshoe-shaped. You were asking about the Musselbruch. This is this one here, right? Like a scoop mark. They can also be kind of like conduit. So there's a whole host of these forms that can be encompassed or gathered and put together in the same kind of category of bedrock erosional forms. So here's where things get a bit more complex and where the controversy also rises a bit. When this French River work was done, so that big outcrop I've been showing you, if you go on the ground, you start seeing the details of the sculpting, and you can see, and we're talking about these delicate rims that are preserved, and you can see the areas of erosion and the moats that are filled with water, these little ponds or little puddles around it. What you also see is that the bedrock surface is covered in boulders. Nothing else. So if it's been abraded by ice, either we expect that there's a lot of removal of sediment and there's not much left on the surface, or we might expect to have a cover of till or outwash, but there's conspicuously, what's absent is everything smaller than some boulders at a critical size. There's what we call a lag of boulders, meaning it's boulders of a given size or class of a given size that are left behind. Everything smaller has been stripped away. And so in that interpretation of these boulders being a lag, the idea is that you had flows moving over that surface, and they were sufficiently powerful to entrain, mobilize, and remove entirely the particles that are smaller than these boulders. So these become essentially markers of a critical velocity of the flows that move over those surfaces. Does that make sense? Mm-hmm. Everything finer gets stripped away, and we leave behind what can't be moved given the velocity that's required to move a boulder like that. And if you look at boulders individually, they're also full of these percussion marks, as if they've been sort of repeatedly hit by other class. So as you're in the process of stripping away all the finer particles, and these boulders are either not moving or barely moving, everything else is shooting by and flowing by, and they're bumping and hitting those boulders, and so those boulders kind of get bombarded with all kinds of other class, and so they get this pock mark and these percussion marks, as they're called. And that's another clue that perhaps these are in fact lags, meaning that they're left behind.
Now, those boulders they're of different composition than the bedrock there?
I don't know. I mean, we're on the shield in this area, I think, and I think it's fairly uniform in composition. I'm not sure.
Okay.
Really what matters, I mean, there's going to be some slight differences in the density of different rocks, but they're not going to be radically different to the point of, really changing the velocity that's required to move.
Right.
Okay.
I guess I wasn't thinking so much that, other than the fact that, how far they had to be transported before they were placed there. Because I think we can assume they're not autochthonous, right?
Not necessarily, though. When you start calling things a lag, the implication is that they haven't moved far.
Okay.
They've basically been stationary because the flow is incapable of moving them.
Gotcha.
But everything else moves.
The fines have been washed away.
Everything smaller is stripped away.
Yeah,
exactly. Though they may have rolled a bit or moved a bit, but
okay.
It's not like we're talking about the sediment load of a river that's traveling.
Because if they have been transported, it's very possible, if not probable, that they were actually transported within the glacier mass itself.
They could be, absolutely. I mean, and they may well have been transported in ice and been deposited at some point or been part of till, but then this water event happens, and then we strip away all the other finer particles that might have been in the till, and we preferentially leave behind these boulders. So we can take their size, we can make a few estimates on their density if we need to, and we can arrive at, we can make some estimates on the velocities that are required to move these boulders. And so it gives us an upper limit on how fast the flows have to be moving to strip these away and move them around. That's, I'm going to say 5 5 to 8 meters per second, maybe a bit more, it might be around 10 meters per second to move them. Now, if you map these broad areas of bedrock that have been sculpted, you realize that this is Georgian Bay, and so this is on land. This is a shoreline essentially around the red line. You realize that there's, first of all, remarkable similarity in the paleocurrents. In other words, if you take the forms and you map their long axes, you get an idea of their direction, and it's remarkably similar across the entirety of this northern part of Georgian Bay. So they mapped them, they being John and I think his colleague mostly, Phil Korth. They map them and they come up with this distribution of these bedrock sculpted areas, and then they argued that there's no real evidence of cross-cutting between the sets of bedrock forms, and they all have really consistent orientations. So by that logic, maybe they all form at the same time. Mm-hmm. In other words, when you produce them, they're what you see in terms of the extent is actually the extent of the flow that makes them, right? If you start seeing cross-cutting patterns or some variation in the direction, perhaps you're looking at different episodes of formation for each one. But in this argument, they're arguing continuity of the development across the landscape, and that therefore they're arguing also that there's a continuity of the flow. The width of the flow is basically the width of the area that you mapped. So you take the width of the flow, you take the critical size of the boulders for a velocity, you have an idea of how deep the flow must have been to overcome some of these escarpments. And if you multiply, or if you do that, if you have those three variables, you can come up with a discharge. You got a velocity, you got a depth, and you got a width of flow. And you come up with numbers that are in the 10 to the 7 sort of range, right? We're basically into megaflood scale discharges in terms of meters cubed per second for discharges. So very quickly, the width here, if you look at the scale, this is roughly 60 or 70 kilometers in terms of the width of the proposed flows to produce these forms. So a 70 kilometer wide flow that's about 10 meters deep and is moving at a velocity of somewhere around 8 to 10 meters per second, if I recall correctly. And if you calculate that, then you'd end up basically if you look at these charts of super floods or mega floods, we're on this end of the chart. We're on sort of Missoula scale discharges going through that area of French River. But I did warn you that sort of this is kind of the controversial parts of it. The most controversial part of this argument in this calculation is the width of the flow. Mm-hmm. It's really is this truly a 70 kilometer wide flow? I mean, if you try to picture that, this is not in a well-established river channel or something like that. This is a transient event where it would presumably be potentially, I mean, if you go from the mapping, 70 kilometers wide. Right?
Which is about 45 miles roughly. 45
miles wide, moving at a velocity that moves everything or strips away everything except the largest boulders we saw in those photos. So, I said earlier that the Meltwater Hypothesis is not something that is widely accepted. It's controversial. And part of the controversy stems from the fact that, the implication of recognizing that some of these forms might be made by water creates very quickly a need for absolutely staggering amounts of water. Like the volumes of water are incredibly large because Georgian Bay is one small part of one of those flow tracks that I showed you on that map earlier, right? It's a very tiny portion of the entire map of drumlins and streamlined landforms across Canada and the Laurentide ice sheet. It's a relatively small area compared to the full size of the ice sheet. And it still requires a discharge on the scale of Glacial Lake Missoula as a point of comparison.
I'll just throw in that 10 to the 7th cubic meters is about roughly 350 million cubic feet per second, which is in the size range of the flow that carved Grand Coulee.
Yeah.
About half of what Vic Baker calculated for the Rathdrum Prairie, Spokane Valley area, but about roughly the same as J.T. Pardee calculated for Eddie Narrows in the Clark Fork.
Yeah.
Just for comparison. And we haven't really talked about that. We haven't really gotten into the scablands yet and the Missoula floods and all of that. But just for comparison, when we come back to it, it'll be interesting to contrast this, when we're looking at pictures of Grand Coulee and the flows, the peak discharges there, the peak discharges through the Clark Fork at the glacial dam outlet, to compare it back to what you're showing us here, that we're looking at roughly 10 to the 7th cubic meters per second. And yeah, like you said, truly phenomenal flows.
And, it's funny you bring up the scablands and Pardee and Brett's, because one of the obstacles, I guess, to widespread acceptance of this idea of meltwater as being this agent of producing these landforms is just the fact that it requires so much water. And so often the argument has been, well, if there's so much water needed, where is it? Where does it come from? Which are arguments that are actually not that different from exactly what Brett's faced in terms of counter arguments to dismiss his idea. He had landforms that he couldn't explain other than, they seemed extraordinary, and there were patterns that he could recognize that were obviously not what you'd expect from a normal river. So he had a huge amount of process-based arguments and field evidence. And the Achilles heel in his argument seemed to be for a long time that he had no water source, or it required so much water. People said, well, how can you produce that much water? Where does it come from, and where is it stored, and on and so forth? And that's exactly what many people have sort of argued, to say, okay, well, if these forms 70 kilometers wide, and then we'll see in a second even bigger with drumlins, that requires lots of water. Where is it? And until you can tell us where it is, where it comes from, and how much there is, and where you store it, that doesn't make, we can't go with this.
Mm-hmm.
So there's some parallels there in terms of the argumentation that's been used to counter some of those ideas.
We've talked about exactly that several times on the show, and
yeah,
the parallels between Brett's reception and John Shaw's reception, and how kind of the criticisms kind of essentially were similar in both cases. Where's the source of the water? And I think, John at one point, I think, tried to invoke a subglacial reservoir, perhaps in Hudson Bay Basin, didn't he? Yeah. And then perhaps kind of played around with the idea of superglacial waters, but without actually coming down definitively, I don't think, on any given source, did he?
Yeah.
Or did he have an idea?
I think he had many ideas, and I think there are different possibilities.
Yeah.
I mean, at the same time, you can dismiss you might want to dismiss the argument to say, well, there's enough landform evidence that sort of points towards water that I shouldn't have to tell you where the water comes from. But it is an issue. I mean, you have to sort of, at some point, you have to face that reality that it requires lots of water. So you can't just not answer or not address that question.
Right. Well, yeah.
But I guess the real challenge is when people dismiss it and say, well, we don't have, for example, analogs of that much storage of water. Okay, well then we get into a territory where, well, who's to say that the analogs we see today, where we have water in glaciers either underneath or on top, are exactly what we would have had as we were deglaciating potentially a very large continental ice sheet.
Right.
So those arguments get fairly complex pretty quickly. But I mean, personally, I think that at some point you have to account for the water. And it is possible that, some of the areas that have been mapped and argued to be major flood tracks, I mean, if you can't supply them with water, then it's difficult to make that argument fully. So there's perhaps some adjustment to be made in terms of the arguments. But, this is sort of going down a bit of a rabbit hole, but you were talking about Brett, so, it's an interesting parallel there. Mm-hmm. And so to your question on what, from discussions I had with John Shaw, he had lots of ideas, either subglacial lakes in different places, superglacial lakes, so on top of the ice. He worked quite a bit for a few years with a colleague or a friend who was in Vancouver, who was a mathematician who kind of got really interested in this question, Ed Shoemaker. And Ed Shoemaker did some interesting modeling where he argued that you could actually pool lots and lots of small puddles of water under a glacier. There's some basic sort of geometric relationships between the slope of the bed or obstacles on the bed and the slope on the ice surface that allow you to pool water. And so instead of arguing or trying to find one gigantic reservoir of water, Shoemaker was sort of more leading towards the idea of having a number of small ones distributed across a very large area. And then all you really needed is some system or some way of connecting them. So you could have water on top of the ice that drains to the bed, something that we see today in Greenland happening almost seasonally. And as that water connects to the bed, it kind of connects all these other puddles together or something like that. And so there was a lot of thought given to that pretty thorny problem of, where is all this water coming from?
Well, it certainly does seem, though, like when we look at the vast scale of the drumlin fields, that what we need is some kind of a chronology. I mean, to what extent were these things happening simultaneously? What extent were they time transgressive?
Yeah.
Did we see the earliest drumlin swarms? To me, I would have to think that it's correlated with the meltwater pulses, because we have at least 3 meltwater pulses. James Teller's work up in the mid-continental region. We've been talking about his work for a couple of episodes now, but the idea, the new work now showing possible catastrophic drainage of Lake Agassiz.
Yeah.
So, draining into the Arctic and so on. I think we have to address this problem in the context of the entire deglacial sequence.
Yeah.
Which I think is clearly not a uniform process. There were discrete events within that melting process.
So, for Agassiz, the drainage is proglacial, right? So it's not the source, or it's not, but I take your point that there might have been earlier events prior to Agassiz that drained subglacially, or even some perhaps after.
And
but
Agassiz
it'd have to be big.
Yeah.
Absolutely. And there's a paper from John had worked with somebody else who was doing some work on coral reefs in I think the Gulf of Mexico, and they were showing episodes of reef drowning and pulses of water essentially coming to the Gulf of Mexico, very large amounts that with timing that might well coincide with some of these proposed big floods.
Yeah, he called them CREs, catastrophic rise events.
There you go.
Yeah. And that's what I was thinking about, is that we need to be looking at these patterns of sea level rise, because clearly that's the ice complex melting.
Yeah.
So we need to be looking at the whole deglacial sequence, I think, to make sense out of this. And all of the evidence for mega floods and drumlins, particularly if they end up being fluvial, and I always tend towards the term glaciofluvial, because that encompasses the whole spectrum of possibilities. Some combination of ice and water, maybe dominant one or dominant the other, but clearly it does involve the presence of the ice, first of all, and then and clearly the ice is gone now, so we know it melted. We can pretty much assume that. So in that process of melting, clearly there's going to be copious amounts of meltwater generated, and this meltwater has to, I would think, leave a geomorphic imprint.
Yeah, and I think the corollary to that is that those events, as they're proposed, they're so big that they would likely have an offshore signature.
Yeah, and exactly.
Right, yeah. And that offshore signature would be, you just got to look at what are your outlets. You've got the Gulf of St. Lawrence, you got the Mississippi, and then you've got the Columbia. We know that Missoula has an offshore record.
Astoria fan.
Exactly. Plus, actually, in British Columbia, there's plumes of fresh water coming during Missoula that travel. Though they don't sink like the turbidity currents that go to the Astoria fan. They actually rise and they disperse in different directions. And so there's
like splayed out from the mouth.
That's right.
There.
Yeah. And then through the Arctic and Hudson's Bay, and there's some. This is yet another rabbit hole of discussion. But the North Atlantic has this really intriguing, enormous submarine braid plane and fan system that comes out of Hudson's Bay. So it's called the NAMOC, North Atlantic Mid-Ocean Channel. It's a very, very large submarine fan. It's hundreds of kilometers in length, and it's extremely coarse. And there's a lot, it's tied, it's kind of implicated in Heinrich events and those episodes, but there's a lot of evidence for a lot of meltwater essentially draining from the ice sheet to form this braid plane, because it's under 4 kilometers of water. It's on the floor of the North Atlantic.
Wow.
And it's sculpted, and it's got levees, got a set of levees bigger than the Mississippi levees. And so there's potentially some offshore records that might point towards some of those major events.
Yeah.
But again, connecting all that through time, as you're saying, the chronology is really critical. And so we're kind of dealing with little pieces here and there and trying to see how we might link them up. But
Yeah. I will interject just for the record that we don't mind going down rabbit holes.
okay,
here.
perfect. Well, there's a lot of rabbit holes.
Well, I've sort of got another one there. I didn't want to interrupt, but you did start to kind of get into it with the subglacial pondings or lakes.
Yeah.
You know, with that previous image, if that's 40 plus miles wide, or you said 70 kilometers, right? I think the obvious question from amateur like me, what's holding up the ice? How much ice? How thick is the ice on top of that? What's supporting the ice? Is it floating in some way? Or,
Yeah.
I mean, that's a huge expanse to not be holding up all that ice.
That's right. And so, so if you start ponding water under the ice sheet, the shear stress at the bed drops down to nothing. And so the ice, if the lake is big enough, the puddle of water is big enough, and it's under sufficient pressure, then the ice essentially floats on top or rests on top of the water. And at that point, it can thin really quickly. So if you envisage that you had an ice sheet where there was lots and lots of puddles of water, however big they might be, you'd expect the ice surface to respond to those pools of water on the bed. And the ice would respond by thinning and flattening. And so how thick was the ice over that area? I mean, that's a very good question. It's tricky to answer that question. I mean, the best we can do on the Laurentide often is try to work backwards from the isostatic rebound of the landscape and sort of try to work backwards to say, okay, how much ice does it take to deform the crust to a point where it'll produce this much rebound after deglaciation? And we sort of work our way back that way. But if you throw in the extra variable of having water pooled under the ice, then the ice thickness might change pretty radically. It would certainly be uneven. Yet with water pooled, you'd still have a load on the crust. So you could still produce some amount of isostatic depression, right? So you could still see the isostatic effect that you have today, but you might be assuming entirely that it's from a load of ice, not a load of ice and water necessarily.
I think the challenging part here, though, is to get the ponded. You have to get the ponded water moving.
That's right. So
somehow you have to integrate the whole disparate mass of separate ponds and then get them moving. And how do you do that?
That's right. So, I mean, if you look at modern environments where we're seeing this happening, Greenland is probably a good example. In Greenland, there are lakes, there are pools of water that form under the ice sheet. They can form, some of them are seasonal, some of them are multi-seasonal. But what's happening more and more, because the Greenland ice sheet is melting fairly rapidly, is you get melt ponds on the surface. And those melt ponds drain through crevasses in the ice. And so it's a bit like a hydraulic wedge. You fill up a crevasse and it produces this lake on the surface. And then there's enormous amounts of pressure at the bottom of that crevasse that's filled with water. And that's enough to actually wedge the ice open to a point where it actually connects to the bed. At some point, it hits the bottom of the ice. And then the water drains like this bathtub straight through the bottom and now flows at the bed. And what you tend to see happen there, in some cases, the ice can lift a little bit, or the flow can spread outside of existing channels a bit. There's just so much pressure and volume of water that it spreads. Some of those drainages make it all the way to the front of the glacier, but some of them don't necessarily. Some kind of flow somewhere and they don't fully exit the glacial system. So there's a lot of complex hydraulics happening in those glaciers. But one way to get, if you're thinking back to, say, the Laurentide ice sheet, one obvious way to initiate a drainage, because that's what you would need. You'd need some kind of trigger to initiate a drainage to produce, to sort of release all this water that would then be potentially capable of eroding some of the bedrock forms we see. That superglacial, that lake on top of the ice connecting to the bottom hydraulically, is a really good mechanism to do that, because that water has got lots and lots of head in terms of being able to connect and then link up lakes or puddles of water and then initiate the drainage. You got to see it as like this dynamic equilibrium in terms of you pool water, but you have to hold the water back, and you hold the water back either because you have fairly thick ice, or you got bedrock obstacles, or you can even have it because you've got some sort of slight temperature differences. But at some point, you can overcome this threshold, and that's what initiates the drainage, right? So there's multiple ways of doing that. In the Cordillera, is another example where it's arguably easier to pond water because you got all these valleys. You could do it because there's a record of, say, volcanoes erupting under the ice. And so that's a mechanism by which you might produce lots of water very quickly, which overcomes a threshold which initiates a drainage.
Okay.
So I think, yeah, you kind of hit that. I think, it has to overcome quickly, whatever. I mean, it has to overcome the threshold relatively quickly. And I know there are some pretty large lakes under the Antarctic ice sheet.
Yeah, there are many lakes under the Antarctic ice sheet. I mean, every year there's more, and there's hundreds of them under the Antarctic ice sheet.
The larger ones, though, tend to be in bedrock basins. They're not actually contained by the ice itself.
Yeah.
You can almost remove the ice and you're still going to have this lake there.
Yeah.
Maybe along the lines of, look at some of the, Great Slave Lake, that was glaciated. Now it's a lake. Was there ever a lake in that basin under the Laurentide ice sheet? I asked that question about Lake Pend d'Oreille and the Purcell Trench Lobe, where I haven't really seen the basin of 1,500 feet deep of Lake Pend d'Oreille. At what point was that sculpted out?
Mm-hmm.
Was that glacially sculpted when the ice dam presumably existed holding in Lake Missoula? Was there a lake? Was there a subglacial lake in the basin of Lake Pend d'Oreille? And I think that's an important question, because not to get off on Lake Missoula now, because I'd like to get back to Drumlins, but my problem there is if you've got a hydraulic head of 2,100 feet on the up glacial side, you've got Lake Columbia lapping at the toe of the ice dam on the other side. And then if there's a body of water under the lobe itself, how do you have all of that water without having hydraulic connectivity between the water outside the dam, the water inside the dam, and the water under the dam?
Mm-hmm.
That's where I kind of get I'd like to talk to some engineers and see what they think about that.
Yeah.
Because that's where I kind of question the whole efficacy of the ice dam model.
Mm-hmm.
But that's a subject for another discussion. I would rather right now get back to the Drumlins.
Back to Drumlins. You got it.
Yeah.
All right. So let's go straight there. Drumlins, we've defined them early on. We're back to them. So we've left those smaller scale bedrock forms. This is forms that are 2-3 kilometers in length. But now that we've looked at the bedrock forms, there's lots of morphological characteristics we can recognize on these drumlins. For example, up here where the A is, hey, look at that. There's this crescentic scour, and they extend laterally into furrows. And if you start looking at that and you stare at it long enough, you start recognizing that actually the vast majority of these drumlins that are now much bigger, they're not necessarily in bedrock. They're not part of these smaller scale sort of rock outcrops that are sculpted. Mm-hmm. They have a lot of those morphological characteristics that we kind of ascribe to this idea of a horseshoe vortex that's a fairly well-established or very well-established sort of hydrodynamic phenomena. And so, a lot of the buildup of this meltwater hypothesis was in part driven by the bedrock sculpted forms, the recognition that there was lots of form similarities between the bedrock forms and much larger drumlins that were not made of bedrock, and the implication being that, hey, if each one of these records the presence of a horseshoe vortex, it basically implies that this entire landscape is potentially flooded and forms underwater, right?
Mm-hmm.
We saw this diagram earlier. So, those form process analogies and connections were present, in terms of the development of this idea. There was more work done on plaster of Paris. So these are negative forms, but you can recognize here that in the plaster of Paris, we've excavated forms that can be both elongate or very broad. So there's some elongate forms, some wide, broad ones. There's some more examples in here. And those forms are remarkably similar to some of the ones you see on the landscape, like these. Mm-hmm. Right, so I can flip back and forth, but and then put the place. But I think this is the Snare Lake Drummond Field in, I think, northern Saskatchewan or Northwest Territories. But if you look at some of these drumlins, there's some really elongate ones, and there's some that are broader, like these, a bit more parabolic in shape, flanked by other ones that tend to be sort of more symmetrical like that. And then we can just go back to what we see in the plaster of Paris, and we see the same sort of spatial patterns and distribution. The scales are obviously totally different. This is 2 centimeters in plaster of Paris, and this is, probably about 6 or 8 kilometers across the picture or something, probably even more than that. So the scales are totally different, but again, we see similarities in the patterns and the forms. So that was very, those form analogies or those similarities were integral to the thinking process or the thought process that went into developing this meltwater idea. If we zoom in a bit, we can see some of these forms in more detail. More examples of drumlins that certainly share morphological similarities to what we see eroded in plaster of Paris when you have water flowing over it in the flume, except that in this case, it's a kilometer long, not a centimeter long. Those forms that I showed you earlier from the bedrock, I'll show you some examples of drumlins that are much more recent. They're on the deglaciated portions of what's in Antarctica and Greenland, so areas that are arguably more recently deglaciated. So these are images taken from swath bathymetry, so shipborne surveys in the ocean that try to image the floor of the ocean. And that the ocean floor was formerly the bed of the glacier, but the glaciers retreated and sea level rose. And so they're essentially flooded landscapes that are the former bed of the ice sheet. But you can see the forms that you see there, like all these drumlins, we can now recognize them. But again, look at these. We've got conspicuous little scours along the front that then define lateral furrows. They're integral to the actual form. They're just so clearly associated with them. The residual only exists because you've scoured and excavated around the front and the sides of it. They're like, they're completely hard to dissociate in terms of the form. And some of those experiments on plaster of Paris, it's what becomes apparent is that the scour and the residual evolve together. So it's not simply, one argument you could make for these forms is to say, well, why don't we just make drumlins first and then have a little bit of water come over the landscape later to just sort of like ornament the front of it, because your drumlin becomes the obstacle and you just sort of like remove a bit of stuff and that makes the moat around the front. So it doesn't require as much water. It's an idea that's been out there. But if you look at those flume experiments, what you see is that the residual and the horseshoe vortex and the resulting crescentic scour, they evolve together. So the scour starts shallow when the residual is small, and as the residual gets bigger and bigger, it's because the trough is actually getting larger and larger. So there's this sort of coevolution of those two parts of the form that just reinforces the idea that they're really hard to dissociate.
How far offshore were those?
That's a good question. They're usually, they can be anywhere between, tens of kilometers to, in some cases, a bit further, but usually within tens of kilometers.
Okay.
But it's actually 10 kilometers across the entire image, right? So again, these are, size-wise, these are certainly drumlins. They're kilometer long or more in some cases. So back to this meltwater model that we started there. So I kind of gave you I hope, a bit of a picture of how it came to be that cartoon arrives at that picture. So we've got the drumlins, we've got what are called cavity fills. So one of the early arguments in the meltwater idea is that as that sheet of water passes over the landscape, it interacts with the substrate, so the bedrock, and it interacts with the sediment that's on the bedrock, but it also interacts with the roof of ice that's overlying it. And it's also capable of sculpting that roof of ice. So what you see in there is that the roof of the ice sheet is actually shaped, and it's shaped by that sheet of water. And it's eroding forms that are transverse. So they tend to be at right angles to the dominant direction of flow. You look at these arrows, they're going top right, bottom left, but then you got these yellow bands across that are transverse. And it's also eroding forms that are aligned with the flow that will then become the drumlins. So what John Shaw's meltwater idea or hypothesis proposes is that you can have drumlins that are fully erosional. You just strip away sediment that's already on the bed of the glacier, or you can have some drumlins that are depositional because you have excavated cavities in the roof of ice, and then subsequently you will fill them as this flow of water starts to wane and decrease in intensity. Then you have sediment that's in transport, and you start preferentially filling those cavities. And so some components of the landscape are actually depositional, not all erosional, not all depositional. I started off talking about how people have been looking at drumlins for hundreds of years, and there's no real consensus. But there's not even clear consensus on the fact or whether or not drumlins are fully erosional or depositional forms. or some combination of both. Now you'd think, if you have a bump on the landscape, your options are either, well, this bump is a residual because I've removed everything around it, or this bump has just been built up because I've had material accumulate. It's not entirely clear. Some drumlins show unequivocal evidence for erosion, because often you have inside a drumlin, you've got bedded or stratified sediment like sand and gravel, sometimes lake sediments. In other cases, they're entirely made up of till, and they could well be erosional or could be depositional. I mean, when you study landforms, that's a pretty basic question to nail down early on. Are they erosional or are they depositional forms? And that's not even something that's that clear when you look at drumlins. There seems to be evidence for both, and in some cases, increasingly, there might be combinations of both processes contributing to the buildup of drumlins and the formation of drumlins.
A few years ago, I was cataloging, I was making charts of various types of megaflood features. And so I had erosional, depositional, and going through, a slot canyon, erosional, a recessional cataract, erosional, a gravel bar, depositional. When I got to drumlins, I had to make a third category that kind of encompassed both.
Yeah.
So.
Yeah, it encompasses both, and it could be probably either or a combination of,
Right. And it's almost like a continuum, and it could be trending towards one end or the other end of the continuum.
Yeah, which raises an interesting question, and that is, is it possible that in our attempts to come up with an explanation for drumlins, we've kind of put too many things in the same bag? What I mean by that is that is it possible that there are either different types of drumlins? Are there some drumlins that form in one way and some that form in another? And when you start trying to come up with an explanation, you go for something kind of unifying, right? I mean, this is sort of part of Occam's razor. You kind of try to come up with the simplest explanation that provides the broadest that can account for the most of the observations. But perhaps part of the issue is that, in the efforts to do that, we fail to recognize that there are some, really distinctive drumlin forms that speak to very unique processes. Does that make sense?
Mm-hmm.
Yeah.
We've sort of mapped drumlins to say, okay, sure, I see that some have a crescentic scour, but not all of them do. And some have different morphologies. And so perhaps there's more than one process at play, and each process is responsible for producing, very unique morphological aspects of a drumlin. Now, these are sort of risky or tricky ways to proceed when you try to understand something that you don't understand well, because Randall could go out and come up with an explanation for his drumlin, and Brad would go for an explanation for his drumlin, and we'd each come up with something potentially different. And we could argue till the cows come home about who's right. The idea would be to come up with an explanation that is able to account for all our different observations. I mean, that's when the person that would come up with the genetic explanation that can account for all the things that each of us has seen individually kind of wins, in a sense that has the most powerful explanation. Otherwise, you can get as many explanations as you got people going out to look at drumlins. And so, but that can also fail, I think, sometimes, in the fact that if we lump too many different types of drumlins together without recognizing that they are sufficiently different to have different processes, maybe we miss something. And maybe that's, at some point, that's where we're at, is that we need to maybe go back and better link the drumlin form to a specific process. Does that make sense?
That not all drumlins are formed by the same phenomena. Is that what you're saying?
Possibly. Yeah. And then then the tricky thing is to figure out what is the piece of evidence that points you towards one process versus another.
Right.
And the risk in doing that is that if you go, like I was saying, if you go out, you might notice something, say, that's the most important part, it points me in that direction. Well, and I could come up with something different. But the day that I come up with an explanation that accounts for both what I see and what you see, well, I've got now something that accounts for the variability, right? So my explanation has a bit more sort of explanatory potential than yours that way.
Right.
Mm-hmm.
So why is this transverse form important? Why are they important? Well, partly they're important because when you look at glacial landscapes, you often see that drumlins also tend to be associated with other types of landforms. So here we've got forms that are longitudinal in the sense that they're parallel to the presumed flow direction. And so they tend to be linear this way from top to bottom, or top right to bottom left. But very close to them, we've got transverse forms that are basically orthogonal to those elongate drumlin forms. And in many places, it's very difficult to find the boundary between those two different sets of landforms. And quite often they'll merge into each other, or it's a gradation between them. And in some cases, we see that those transverse forms kind of have an overprint of longitudinal forms. Okay, so these are called rogans, just to keep the name that we use at the start. Well, often you see drumlins overprinting the rogans. And when you trace the rogans laterally, you realize, well, they kind of gradually morph into drumlins. And so when you start seeing that and no clear break between, you're thinking maybe these are kind of a continuum of forms. Maybe there's a process, as we're just saying, maybe there's a process that's capable of producing both transverse forms in one moment or one location, and elsewhere longitudinal forms. And in the transition, maybe one kind of piggybacks on the other because that's part of the continuum. So the Meltwater hypothesis was sort of trying to get at those spatial relationships and those continuum, the continuum of forms. So we have transverse, these rogan, that in some cases might be genetically related to some of the drumlins.
The rogans look like they would have something to do with a regular oscillation of like up and down
it's a wave
flow.
Yeah.
Once you get into that rhythm of where the water's moving in this rhythm up, down, then you would seem to get these ripple.
That's right.
The first thing,
distances.
the first thing that would come to my mind is that perhaps you've got a continuous flow, except that you've got this glacial lid on the drumlins and you've got a free surface over the rogan. Because I think the rogan, I think we can see examples of that in rivers and things that we know it's a free surface.
So you can certainly produce that.
That would be speculative, of course, but
you might produce that. But you can also, in this case, the rogans are there because they're essentially infilling the cavities that have been eroded into the ice, in the roof of ice. So they're fill. And that was during the break we were chatting about the fact that if you cut river ice in the winter and you flip it over, where the water has been flowing under the river, it's actually been sculpting the underside of the ice cover, and the underside of the ice cover looks an awful lot like what you start seeing in terms of the patterns of rogans. Now, the prediction that comes out of that is that if these are infills, you'd expect them to be composed of somewhat sorted sediment. They're filling with the sediment that's in transport in the sheet of water. And so you'd expect some sorting, maybe some stratification. And indeed, some rogans do seem to contain that kind of material. So, if you think of what the hypothesis is predicting, there's been some documented rogans that contain sorted and stratified sediments. But inversely, there's also been some rogans that contain till dominantly and might point more towards a process of erosion, not clear deposition and infilling of a cavity. So again, we're sort of in a scenario where there might either the model to explain it doesn't work, or there's more than one model at play, or there's more subtleties we're missing in terms of how we might account for some of the materials. You can take that continuum idea of landforms, you can actually stretch it even beyond that. If you're on the prairies in many places, and a lot of this work was done in Alberta early on, so there's a lot of pictures that come from the prairies of Canada, but that's where a lot of the work and some of John's students work. But many glacial areas have hummocks. They have areas of very bumpy, irregular topography characterized by depressions and little residual highs. And often those are assumed to represent stagnation of ice. When you have a glacier that's decaying, it's covered in sediment near its margin, and it can often sort of melt in very irregular ways. And so that the sediment that's in the ice and on top of the ice kind of gets let down irregularly and creates this hummocky, bumpy surface. So hummocks are often thought to record stagnation zones near the margin of the glaciers. But if you look in the prairies, there are hummocks here that are closely associated with some of the Rogans and some of the drumlins that we see on the prairies. And one of John's students, Mandy Monroe-Stashik, did a thesis on some of the hummocks in Alberta. And what she was able to show quite clearly is that, there's the hummock form. I'm talking about bumps and irregular surfaces. There's one, there's a depression in between, there's another. But what's important is that everything that's inside the hummock is actually truncated by the hummock surface itself. So you can imagine, or you can try to picture in your mind that if you had sediment that is being let down very irregularly, you would, first of all, probably start obliterating or breaking down any of the structures or the bedding that you might have in that sediment, if there is any. But you'd also end up with a surface where the hummock surface and the sediment inside are clearly not a truncation, right? This is an erosional surface. In other words, the hummock form is something that has been carved out of pre-existing material, right? Does that make sense? I mean, this is a fairly clear example of where you can see, you can follow the bedding or the structures in the hummock, and you can see that they basically end abruptly at the hummock surface, which is often a pretty good sign that surface is erosional. More examples of a hummock with some, in this case, inclined bedding, but it's truncated at the surface. So on the prairies, there was some of this evidence suggesting that some hummocks may not be markers of the margin, but are in fact erosional forms, not simply just stagnation and decay of the ice, but erosional forms. And they're also part of the continuum of forms that are produced by this meltwater flood. I think I have the right map. Yeah, so if you look at those hummocks, they're the green areas in Alberta. This is an early digital terrain model of Alberta. The Rocky Mountains are on the left here of this picture, okay? And I remember you guys went to the Okotoks erratic down here, okay? So these green patches are these belts or groups of hummocks. And interestingly, they're on uplands. They're on summits, they're on highs. They're not in the low spots where you might expect ice to be stagnating or in a band near a presumed margin. They're actually on fairly prominent highs, and they have this morphology where you tend to see that surface is erosional. So as part of that meltwater idea, the continuum was expanded to account for these hummocks. If you look at these maps of Alberta, let me go back here. Early on, John Shaw and his colleague, as they were developing the idea, they started mapping flow path. They said, hey, if we're going to argue that some of these drumlins are recording large amounts of water, what pattern are they following? And so that's what they were mapping here. These arrows are mapping what they called to be the major flood tracks through Alberta in this case. And between these major flood tracks, we have these uplands, these residuals where we have hummocks. And the idea is that you get hummocks early on in the process of erosion when the flows the meltwater flows are fairly energetic and high. And gradually, as they wane a bit, they start to channelize and they focus into these major flood tracks. Okay, so there was this expansion of the model, if you will, of the hypothesis to try to incorporate as many of the glacial landforms that you could see in the landscape, because there's some real odd observations, like the fact that the hummock surfaces were truncated. We were talking about the kind of the implications of this meltwater model, and I did say early on, I think that this is by no means sort of settled or that it's popular or widely accepted. I mean, there's a lot of resistance to it, and part of that resistance stems from the fact that very quickly, as you start mapping drumlin fields or groups of drumlins, if you argue that they are entirely produced by meltwater, the quantities of water is required are absolutely astounding. Because now, if you look at this map we saw early on, every one of these yellow sort of groupings or belts would represent, a flood path, a meltwater flood path, and in many cases, the width of those flood paths are hundreds of kilometers. The Georgian Bay examples, French River area that I was showing you earlier, they're down here. I told you that 70-kilometer wide flow that is controversial in terms of trying to understand the discharge that's associated with it. That is barely like an area the tip of my cursor in size.
Wow.
And then you scale up to some of these and you realize, wow, for lack of a better word, wow, that requires just, so much water. And we can play the Brett's card to say, well, that doesn't invalidate the entire hypothesis, which I think is true, because there's some pretty strong landform and process connections, especially with the horseshoe vortex for those drumlins that do have the crescentic scour. But nonetheless, you can't, like, the question of the water is a perplexing one. I mean, it's a big one. It's a big open question that needs to be addressed one way or the other. Either you got to find a way of having that much water, or perhaps the hypothesis has to be shifted or adjusted for processes that require less water, or something along those lines, somewhere in between. I'm not sure, right? I'm at the point, I've been working on these questions and thinking about this for a long time, and I'm kind of sort of in that position where, like, I understand the physical and the landform evidence, but I'm also completely perplexed and flummoxed by how much water that requires.
Yeah.
And it's a question that goes beyond, like, you have to produce it, you have to store it, and then you have to release it. So, that those three questions can all go together. And the production and storage is probably the most complex ones. So
that's a good place to leave
stop,
us
maybe,
something to ponder there.
Yeah. I'll stop the share real quick. I might find one or two slides that you might want to see, but yeah, so maybe that's a good place to stop, because there are certainly other hypotheses out there. The Drumlin question is one that's still active, and there's some new ideas that are coming out, different models. When you start generating ideas of how landforms are created, you can come up with sort of scenarios in your head, but at some point you kind of have to confront them to the reality of what's actually going on at the bed of a glacier. And so if you look at modern environments, you could say, hey, why don't we go look at modern glaciers, and do they make drumlins? Well, some do. I mean, the closest thing to somebody observing a drumlin actively forming is probably in Iceland. There was a study a couple of years ago, or a few years ago, that came out. And since then, there's been a process explanation for some of these models. And it does involve water, but nowhere near as much as what the meltwater hypothesis would certainly suggest or propose. And that water is important for flushing out some of the sediment, but it's also a model that proposes deposition, so not entirely erosion. I can show you real quick some of those images from Iceland. There we go. So this is this glacier in Iceland called Múlajökull, and the glacier has retreated and has revealed this belt of drumlins near the front. So they're ringing the front of the glacier. All the red ones are the drumlins that have been mapped. And the glacier's in a retreat. So prior to that, those drumlins were covered, right? So it's through the retreat that you're able to see where they are. And this is arguably the closest thing to somebody observing active drumlins forming. There are a few other examples from Antarctica. I talked about, what do you do when you're trying to understand what's going on at the bed of an ice sheet, like in Antarctica, when there's 5, 6, 7 kilometers of ice between you and the bed? You can't access it, so you have to use geophysical tools. So this is an image made with what's called an ice penetrating radar, and it has elongate bed forms, much like drumlins. And you'll notice that, there's forms that we're now familiar with, like these scours in the front. You see there's a moat in front. There's a moat in front here, and it extends laterally along the flanks. The residual, or at least the form, is defined by the fact that it's got these depressions all the way around the front and the side. So in a way, if you go one more, this is in Antarctica as well. Whatever mechanism is responsible for making drumlins, whether it's meltwater at the scale of what Shaw proposes, or meltwater at a smaller scale, or some combination of various processes, whatever it is, it needs to be able to account for what we observe. And what we observe, in a lot of places, not everywhere, but in a lot of places, and for some drumlins, are these moats. Look at these, for example. There's an example again. This is in Antarctica, fairly recently deglaciated area. we clearly see the elongate drumlin-like form, but we also clearly see the fact that there's a major depression in front of it. Now that depression, if you look at the depth scale, that is a total of like 40 meters, 120 feet deep. And that's a major
That is
erosional form, right? I mean, that's in front of that obstacle, and there's another one here. So whatever's going on, and I can't, obviously pretend that I know whatever's going on, it's going to have to be able to account for those types of features. It's going to have to be able to account for the spatial patterns we see. It's going to have to be able to account for the different types of forms that tend to occur together or in this continuum. So there's a lot of questions. Do you think
that it's possible that when the ice is pushing up against an obstruction, that say if the glacier is moving and the portion of that obstruction sticking into the ice is creating really high pressures on the upstream of the ice end, and that actually melts the ice temporarily and it squeezes past and maybe excavates a little bit at a time, but it could be high speed flows of just the when the glacier slips a little bit against it, maybe. I don't know.
So that's a really good question, because what we see, in Antarctica, there are episodes where that glacier is moving very quickly. We call these either surges, or these are parts that we call ice streams, the zones of the ice sheet that are moving really fast. But elsewhere, or almost anywhere where the glacier is moving over a hard bed, it does encounter bumps, like there's obstacles, and that's what you see, exactly what you described. It's called pressure melting. So the ice presses against the obstacle that offers resistance, and the ice actually melts. And it melts, and it can flow around the obstacle, and it can refreeze. So you do get sort of a net transfer of mass, but it kind of changes phase from the ice to the water to refreezing.
Right. So I wonder if that can actually excavate the front side of it.
As far as we can tell, not really, because those flows are very thin, and they don't involve lots of water. And even if they do involve, cumulatively large amounts of water, that water's not moving very quickly. We still have to be able to move boulders. We might be able to entrain a few clay particles and stuff, but it's not going to be a process by which we're going to be excavating, gravel-sized fragments and a lot of sand and that kind of stuff. So there's a bit of a disconnect there in terms of, the velocities that are needed and what you might expect from that process of pressure melting. If that makes sense.
Yep.
So there's a lot of stuff to think about. There's a lot of variables at play, and there's some that we understand well, there's some we understand not well, and there's probably some that we don't even know we should think about. Or there's some,
We've had to go Donald Rumsfeld several times.
I didn't want to say it, but
The unknown knowns.
And the unknown unknowns.
The unknown unknowns. Yes,
exactly.
Exactly.
But
that's awesome, Jerome.
Like I said earlier, whether that idea in its entirety is right or not, what it does or what it's done is it just raises so many questions. It makes you think about, how much water do we have under the ice sheet? There's a lot of predictions that were made early on that end up panning out. When the Meltwater Hypothesis first started, there was an inkling that there was some water ponded underneath Antarctica in a few spots. There were some radar surveys that had revealed flat spots, and people had argued that there's a lake underneath there. But then, over the last couple of decades, there are so many lakes in Antarctica. Our understanding of the hydrology of Antarctica is changing on a yearly basis. Same with Greenland. And there's a lot of those ideas that, though not exactly the same, do converge a bit on some of the predictions that were made. The work that Ed Shoemaker did on modeling puddles of water into the ice sheet, that's something that recently, with the advent of LIDAR, people were able to map, for example, areas where there's clearly pooling of water in some parts of the landscape in Alberta, exactly where the Meltwater Hypothesis was being developed. Now, that is not necessarily a piece of evidence to say that, it's not a smoking gun to say, well, that completely validates the whole Meltwater Hypothesis, but it does highlight the fact that when you have these ideas that become problematic, or at least, challenging to the way people can consider a problem, it forces all kind of thinking that never would happen otherwise. And there's a lot of value to that. And I'm not trying to be pedantic about the way it, how I'm saying this, but like it's part of the process. Those kinds of ideas that are unusual and a bit out there, they do have a lot of value. If Brett's hadn't come up with his idea, we may well be thinking that the scablands are a fluvial system, right? And not a flood system. Probably not, but somebody would have clued in at some point, but who knows, right? So it's that kind of the research of the science is a process, and that those big ideas like that end up being they're really important part of the process, I think, because they really force you into recesses of your thinking that you might not go to otherwise.
I think it was William Davis, the godfather of geomorphology, that made drew attention to the value of the outrageous hypothesis.
Yeah. So that would be, the Meltwater hypothesis falls in that category of outrageous hypotheses.
Mm-hmm.
Right? And Vic Baker has written a lot on the value of outrageous hypotheses too, in terms of how they stimulate thinking and, why you shouldn't squash them necessarily, but you want to basically deal with them within, reasonable bounds in terms of your understanding in the field.
Right. All right.
Jerome, that's just an outstanding lesson. We're so grateful for you to be able to spend a couple hours with us, and
that was fun.
We'd love to have you back. We didn't even really get into much speculation with Randall, and you guys do some back and forth. So
that's going to be for next. We'll do that next time.
Yeah,
man, I learned a lot.
Perfect.
Thank you very much.
That was fantastic.
That's good.
Mm-hmm.
We just did the Laurentide, then we'll get into the Cordillera.
All right.
Just scratching the surface.
Scratching the surface.
Some similarities, but some differences too.
Sure.
Right.
In some ways.
Yep.
All right.
All right.
Well, thanks everybody for joining us. And this is great. We'll hopefully be doing this again soon, and can continue exploring some of these mysteries of life on Earth.
That's right. And check the show notes for links and relevant information. All right. Thank you guys very much.
And your t-shirts.
And the
Now
t-shirts.
available in stock,
Yeah,
ready for
look at
shipping. I will put a direct link.
The t-shirts are going to help us kick up the funding. We're looking at trying to take this to the next level, which mainly means getting out in the field, more field trips. Once everything has kind of opened up again, we were already had to postpone 2 field trips that we had planned.
Yep.
So we're going to be ready to go when finally we can go.
That's right.
Definitely.
All right, gentlemen.
Send you one, bud.
Okay, well, thank you.
Good one, too. You bet.
Yeah.
All right, guys.
Good to meet you all. Take care.
Thanks. Yeah.
Good night.
Thanks
you.
again,
All
Jerome.
right. Yeah.